welcome to the lecture on learning to quantify. Let's say, this lecture is not really specifically about deep learning. It's about machine learning. It's about a specific task in machine learning called quantification that hasn't received much attention up to now, but it's quite important in a number of application fields. It's actually also a task on which deep learning hasn't been tested much. Okay, so there are just a couple of papers around about deep learning in quantification. So this might mean that, for all of you who are interested in deep learning, there might be a few low-hanging fruits to pick, some good opportunities in application of deep learning to quantification. So the goal of this lecture is essentially, to raise awareness about this task and to help you identify where the potential might be. Let me check. I can't. Okay. So what is quantification? Essentially, in classification, in many applications of classification, the real goal is not really determining the class label of a specific individual, but it's in many cases it's determining the relative frequency of each class in the unlabeled data. What statisticians call the prevalence of the classes in the unlabeled data, and this is called this task, of determining the prevalence of the classes in the unlabeled data is called quantification, or sometimes it's called also supervised prevalence estimation. So let me give you a couple of examples. Okay, so for instance, if I wonder, among the tweets concerning the next US presidential elections, what is the percentage of pro-Democrat ones? So this is a case where quantification is involved, okay, because we are interested in determining the relative frequency of pro-Democrat tweets, Among the posts about the Apple Watch 3, which have been posted on forums, what is the percentage of very negative ones, And how have these percentages evolved over time in recent times, So this task is one that has been studied within machine learning, within data mining, information retrieval, natural language processing in the last 15 years or so, and has given rise to a number of learning methods and a number of evaluation measures which are really specific to quantification. So quantification is nowadays viewed as a task in its own right and not just as sort of a byproduct of classification. Well, as in classification, there are many different forms of quantification. So it may come in binary form, in single label multi-class form, such as when you have more than two classes, but you need to pick exactly one for each individual. In multi-label multi-class form, as when each item may have more than one class attached to it, or in ordinal form, as when the classes, there is a total order defined on the classes. So in general, quantification may also be defined as the task of approximating a true distribution by a predicted distribution. So here we are seeing a plot. Where, let's say, a histogram, where the blue bars actually represent the true prevalence values of a certain data set across 5 different classes, from very negative to very positive. So for instance, here we are seeing the fact that about 45% of these product reviews here, we are talking about product reviews derived from Amazon. So about 45% are very positive, And we're also seeing red bars, which represented the predicted prevalences. So for instance, this quantifier determined that 48% of the reviews were very positive. So you may realize, that the perfect quantifier is one which is represented by a histogram in which the blue bar is identical to the corresponding red bar. And the discrepancy between blue and red is actually the quantification error. As a result, most evaluation measures for quantification are divergences. So divergences are a class of mathematical functions that evaluate how much two distributions diverge from one another. Okay, and so here we are going to use them in order to evaluate how much a predicted distribution diverges from the true one. So why do we need to perform quantification? Well, the need to perform it arises because of so-called distribution drift, which is also called distribution shift. So that's a phenomenon that has to do with the presence of a discrepancy between the class distribution of the training set L and that of the unlabeled set U. Okay, so here we have a display of a plot that shows the presence of distribution drift. So the blue plot, the blue line, represents the true prevalence of a certain class. It's called even E21. That's a class, a code from the RCV1 dataset, which is a very famous dataset for text classification. So we have one class, E21, and we have data collected across 52 different weeks, which are represented on the x-axis, and on the y-axis we represent the prevalence of the class across these weeks. And you can see that there are lots of up and downs. Okay, so in certain weeks that class is very prevalent, in other weeks is less prevalent. Okay, so what is essentially to note is that the blue line is not a flat line. It's not a flat line. So the prevalence is not constant across time. And the goal of a quantifier is to actually follow that line. To predict the oscillations up and down of this line. Okay, so in a sense, here we have three other lines, blue, orange, and green, and these represent three different quantifiers. And of course, the best of the three is the one that fits the blue line most closely. So where does distribution drift derives? Okay, so it may have different causes. Okay, so one is, say, when the environment is, as we say, not stationary across time or space, and or other variables. And the testing conditions cannot be reproduced precisely at training time. So assume that we have a data set of journalistic news, okay, and they date from early 2001, So, before September 11, there used to be very few articles in newspapers about terrorism. But in October, say, after September 11, there are many more, So in the months before September 11, the prevalence of class terrorism was very low, and it is very high in the months just after. Okay, so here we are in the presence of an environment which is not stationary across time. Okay, but it's across space. Other variables is the equivalent problem. So a second cause may be the fact that the process of labeling training data may be class dependent. Okay, so assume that we have to build a quantifier or a classifier that detects rare illnesses, a 1 in a million illness. Okay, so if we take a random sample from our dataset, we might end up with a dataset that contains one positive example and a million negative examples. So we are not going to build any good classifier or quantifier out of it. Okay, so in order to build a good classifier or quantifier, we need to take as many positive examples as possible and remove a sizable amount of negative examples. In this way, the training set is not just a random sample from our distribution, and the kind of test data, the unlabeled data to which we will apply, will have different prevalence. Okay, so in a sense, this training set is biased by construction. This is what people call sample selection bias. Third cause may be that the labeling process itself introduces bias in the training set. Say if we use active learning. When we use active learning, our training set is anything other than a random sample of our distribution. So we are going again, to find characteristics or prevalence values, which are very different from the ones in the unlabeled set. So, whenever we have distribution drift, this clashes with the so-called IID assumption, the assumption that our training data should be drawn identically and independently from our distribution. And this is an assumption on which standard machine learning algorithms are instead based. So we have a problem. So this plot actually shows a number of cases of distribution drift. In the top left, what you're seeing is the distribution of data in the training set. So here we are assuming that we have a single independent variable x, which takes values between 0 and 1. And we have a dependent variable y, which also takes values between 0 and 1. So that's a case of regression instead of classification. So look at this. So suppose that this is a training set. In the top right, we have a test set where we have no distribution shift. Okay, so we can see that the data are distributed very, very similarly to the data in the training set. Instead, in the bottom left, we have a case where we have distribution shift, but no so-called concept drift. Why we have distribution shift? Well, it's the data follow a different distribution concerning the x variables. Okay, so you can see that the x variable is distributed differently than in the training set, but the functional dependence between x and y is essentially the same. So we have distribution shift, but no concept drift. What is concept drift? We have concept drift here in the bottom right panel, where the distribution of the x variables is pretty much the same as in the training data, but the functional dependence between y and x is completely different. This is a much more harder case, to deal with, for both classification and quantification. And, in quantification, we tend to deal with cases like this, presence of distribution shift, but no concept drift. So, the big question is classify and count the optimal quantification strategy? Classify and count means essentially take a classifier, classify all of your unlabeled data, and count how many have been assigned a given class, and that's your estimated prevalence. No, the answer is no. This is not the optimal quantification strategy. Why is this so? Well, the reason is that a perfect classifier is, of course, also a perfect quantifier. Let's say a perfect estimator of class prevalence. That's obvious. Okay. The problem is that a good classifier, a classifier that is good but not perfect, is not necessarily a good quantifier. And I've shown this little example in order to show this. Okay. So here we have two classifiers, A and B, and once applied on the same test set, A delivers 18 false positives and 20 false negatives. B delivers 20 false positives and 20 false negatives. So which is the better classifier? Better classifier is, of course, A, because the total number of errors is smaller. Okay. But what is the better quantifier, the better estimator of class prevalence? It's actually B. Okay, because in a sense, when it comes to estimating class prevalences, false positives and false negatives compensate each other. Okay, so indeed B, in this case, has behaved like the perfect quantifier, has estimated the class prevalence perfectly. Okay, so as an estimator of class prevalence, we should prefer B, while as a classifier, we should prefer A. So this actually means that quantification, this is a proof that quantification should be studied as a task in its own right. We shouldn't just take our best possible classifier and use it to do quantification. There is another observation that shows that we should consider quantification as a task on its own. Okay, and the key observation is the fact that classification is a more general problem than quantification. because, once we have a classifier, we also have a quantifier. We can use a classifier in order to do quantification. But if we have a quantifier, something that estimates class prevalence, we cannot necessarily use it as a classifier. Okay, so classification is more general than quantification. And here, Vapnik's principle tells us something. Okay, so this is a principle which was elaborated by Vladimir Vapnik, the well-known inventor of SVMs, who said something like this: if you possess a restricted amount of information for solving some problem, you should try to solve the problem directly and never solve a more general problem as an intermediate step. It is in fact possible that the information available in your restricted amount of information is just sufficient for a direct solution, but is insufficient for solving a more general intermediate problem, So this principle suggests that we should solve quantification directly without solving classification as an intermediate step. And the goal here is to, of course, achieve higher quantification accuracy than if we opted for the indirect solution. So what are the applications of quantification? There are many, okay? But I want to highlight in particular the fact that there are many fields of human activity which are not concerned with individual data. They couldn't care less about the individual data, but they are concerned with aggregate data only, sometimes broken down according to different variables, so age group, gender, religion, etc. Examples of such fields are, say, epidemiology, Epidemiology is the branch of medicine that has to do with the spread of illnesses across a certain population, The social sciences, the political science. Social sciences has to do with, again, estimating indicators of, say, well-being across a certain population, okay, without caring about the individual, Political sciences is the same, Market research has to do with modeling consumer behavior, again, across a population, but not for a specific individual, Ecological modeling, drawing models of ecological variables across a certain population of living beings, for instance. So these are all fields, which are concerned with aggregate data only. And these well characterized by what two social scientists, Hopkins and King, said in a paper 10 years ago, in which they said, well, in other fields, other people may be interested in finding the needle in the haystack. But social scientists, and I would say epidemiologists and market researchers, are more commonly interested in characterizing the haystack, okay? No interest in the needle. So here we have an example, okay? So this is a plot taken from a paper from computational social science, okay, in which the authors try to establish the temporal trend in the proportions of tweets that supported or opposed the military intervention in Egypt during the Arab Spring, okay? So you can see here an interest in monitoring prevalences across time, and no interest in individuals. Here we have a similar application in ecological modeling. Here these people, these authors were interested in, let's say, trying to monitor or to estimate the prevalence of different species of living beings on the seabed, on the bottom of the sea, okay? So, trying to figure out whether what is the percentage of the seabed which is covered, say, in coral or in weeds of different types, etc. And why did they use quantification? They used quantification because, they collected training data, okay, in certain locations, which are represented here with red dots, and then, used the classifiers or quantifiers that they developed, in other locations, Okay, and it's quite clear, that the distribution of living species, that live off the sea in Barbados may be different from the distribution of species that live on the coast of Nicaragua, and because of this, there is distribution shift. Okay. Here we essentially have from the same work, the result of their investigation. So we have different samples which are represented on the x-axis, 17 different bars, and we have they essentially monitored the prevalence of I guess 32 different living species in this seabed cover, with the different colors representing the different species. So, I mean, these are examples from fields, which are inherently interested in aggregate data. But there are also other fields that are not necessarily interested in aggregate data only, Also in other fields, I mean, there is a benefit to be drawn from quantification. So, for instance, natural language processing. So some authors, for instance, use quantification in order to tune a word sense disambiguator to train on a certain domain, to tune it to a different domain, which was characterized by different sense priors. Sense prior is essentially the percentage of the occurrences of a certain word that have a certain sense. Okay, so for instance, bank may have a sense as a financial institution, or may have a sense as a hydraulic engineering artifact, such as a riverbank. Okay, so we have different senses and different prevalences of these senses in these different domains. Also, in general, I mean, machine learning is a discipline which has interest by itself in quantification, because you may want to estimate the class prevalence of the test set in order to improve the performance of classifiers trained on data with different class prevalence. Okay, so the idea here is to use quantification in order to improve classification. Why is this so? Because in a sense, I mean, when you train a classifier on training data where, let's say, your positive class has a prevalence of 10%, and you deploy your classifier on unlabeled data, on test data, where the same class has a class prevalence of 40%, your classifier is not going to work well. And this is especially evident if you look at the formula of the naive Bayes classifier, where the class prevalence, which is estimated on the training set, is a parameter of the classifier. So it occurs on the right-hand side of the equation, So, if you can use quantification in order to estimate the class prevalence of the test set, you can tune your classifier to behave better on your specific test set. There are, of course, I mean, many other applications. Okay, so I just wanted to mention a couple of them. Say, estimating the proportion of no-shows within a set of airplane bookings. So to figure out what is the percentage of people who have booked on a certain flight which will not show up, so that the airplane company can, let's say, optimize its overbooking policy, or also estimate the proportion of different types of cells in blood samples. Okay, so we have just seen lecture on image segmentation, and figuring out the cells in blood samples is an application of that. I wanted to speak about evaluating quantification a bit. So evaluating quantification means essentially measuring how well a predicted probability distribution, which is indicated with this hat symbol, a hat PC, fits a true distribution PC. Well, in mathematics, the goodness of fit between these two distributions, as we have mentioned, can be computed via divergence functions, which are error functions, okay, which enjoy these two standard properties. So a divergence is any function between two distributions that enjoy these two very well-known properties, identity of indiscernibles and non-negativity, which basically characterize this function as an error function. But also divergences can either enjoy or not enjoy these three next properties, okay? Impartiality, relativity, and absoluteness. Impartiality essentially means that if a divergence enjoys impartiality, then it penalizes equally overestimation and underestimation. And this is, a property that we would like to have in any kind of application of quantification. Relativity essentially is a property that says, well, if divergence enjoys relativity, then it penalizes more, a certain error when it is committed, when it is made on a class whose true prevalence is lower. Okay, so assume that we want to quantify rare illnesses. If we make an error of say 1%, then it's much more serious. If we have a very rare illness, maybe this illness is 0.5% in reality. Then if we have a very common illness, say 0.30%, it's quite clear, that the error is much more serious in the first case. Absoluteness is the opposite, Basically, a divergence enjoys absoluteness if it penalizes a certain mistake independently of the true prevalence, okay? So a mistake of 1% is evaluated alike if it affects a true prevalence of 0.5% or a true prevalence of 30%, So, there are we typically use different types of divergences for evaluating multi-class quantification. Three of the best known ones are the ones that I've listed here: absolute error, relative absolute error, and Kullback, the very famous Kullback-Leibler divergence. So essentially, these are measures which, let's say, typically are averages across all of the classes in the set of classes, And absolute error basically looks at the difference, the absolute value of the difference between the prediction and the gold standard, While relative absolute error basically relativizes this difference to the true prevalence. Essentially, what relative absolute error does is to, let's say, build in the relativity property by construction, And in the same way, absolute error which doesn't do this has, the absoluteness property built in, by construction, Here you can see, the three properties, about the three properties we have mentioned earlier, which measure enjoys which property, And something which we see here is that, say, the Kullback-Leibler divergence enjoys none of them, And this is why, in a recent publication I've done, I've said, I've stated that Kullback-Leibler divergence should be deprecated as an evaluation measure, because impartiality is a property we always want in any applications of quantification. And, depending on the applications, we might want either relativity of absoluteness. Indeed, it has been shown recently in my publication and others, a number of facts about evaluation measures, okay? So, it has been shown that in some applications, relativity is desirable, while in some other applications, absoluteness is instead desirable, and they are one the contrary of each other. Okay, so no measure can enjoy both at the same time. This means that different evaluation measures are desirable for different applications, and this means that essentially when you want to evaluate the performance of your system on a certain application, you have to understand really what that application wants, in order to figure out what is the evaluation measure you want. Not all of them are good for all applications. Another thing that has been found out is that there is yet no perfect evaluation measure, one that satisfies all of the properties that might be desirable in a given application. And currently, the ones that are considered most satisfactory are absolute error and relative absolute error. So I haven't mentioned other measures exactly because these two are considered the best ones. Why instead, as I said, KLD is something that should really be deprecated. Here, I guess I want to skip 2 or 3 slides about evaluation. Just comment on this one. So this is a nice way to plot the quantification error, and I want to explain this plot. Essentially here, this is a sort of a standard way to plot quantification error, in which, well, the idea is that we take a data set, and we generate many different test samples out of it. Because we want different test samples to exhibit different values of true prevalence, different values of distribution drift with respect to the training set. Here, for instance, we had a test set, a training set, and a test set that exhibited a prevalence of roughly 90%, and we wanted to test how good is a quantifier when confronted with a test set whose true prevalence is, say, 0.4 or 0.6, because, when it is 0.6 or 0.4 or 0.2, the value of distribution drift tends to be more extreme, So we want to actually stress test quantification systems, And so because of this, people tend to take a data set, extract different samples characterized by different values of class prevalence. So we are talking about binary quantification here, and test the quantifiers on all these different samples, Of course, if on the x-axis we have the true prevalence and on the y-axis we have the estimated prevalence, the best possible quantifier is represented by, the diagonal line, by a quantifier that always returns an estimated prevalence which is equal to the true prevalence. Here we essentially tested 9 different quantification systems characterized by or indicated by different colored lines. And the idea is that for each system, the color line is the average performance, while the colored band around it represents standard deviation. So the best quantifier is the ones whose colored line is closer to the diagonal and whose colored band is the less thick one. I want to mention, a number of quantification methods. How do we do quantification? How do we generate, quantifiers from training data? In these last 15 years, a number of methods have been proposed, and they can be characterized according to these different classes. Okay, so we have two main classes: the aggregative and non-aggregative methods. So the aggregative methods are the ones that require the classification of individual items as a basic step, while the non-aggregative quantifiers are the methods where quantification is performed without performing classification. And as you might realize, the non-aggregative ones are the ones that where Vapnik's principle is fully materialized, okay, because we don't use classification as an intermediate step. The aggregative methods may be further subdivided into ones that use general purpose learners, the typical learners we all know and love, which were originally devised for classification. While there are another classes of methods, the methods that use special purpose learners. Okay, so the ones that are especially devised for quantification. So what are the known quantification methods? There are several, I've listed, I'm dealing with just a handful of them here. Classify and count, well, that's the sort of the trivial baseline that we want to consider. It consists, as I said, in generating classifier from the training data, classifying the items in the unlabeled data, and estimating the prevalence of the class CJ in U by counting the items predicted to be in CJ, where DJ, this variable, means a decision for class J. So basically the document has been assigned to class J by the classifier. So the notation basically says, the estimated prevalence hat P of class Cj in the unlabeled data according to method CC is equivalent to the probability of the, let's say, to the class frequency, to the frequency of the documents that have, to which class J has been assigned, As we said, a good classifier is not necessarily a good quantifier, and classifying count suffers from the problem that standard classifiers tend to be biased. They tend to be tuned. They are also always tuned to minimize, let's say, the sum of the mistakes or a proxy of this measure, but not, what we would really need, So the absolute value of the difference between the false positives and the false negatives. So for instance, in experiments that we ran some time ago, massive experiments, more than 5,000 test sets, averaging more than 15,000 items each, we found out that a standard linear SVM brought about a ratio between FP and FN of 0.109, while, for quantification, the optimal ratio should have been 1, equal number of FP and FN. And this derives from the fact that classifiers which are optimized for standard vanilla accuracy or proxies of it, such as, hinge loss, they tend to generate many more false negatives than false positives. Let me skip PCC. Another interesting quantification method. It's so-called adjusted classifying count. So it's a method which is based on the observation that after we have classified the unlabeled documents in U, this equation holds. Basically, it says that the frequency of the frequency of the documents that have been assigned class J are a summation across all of the classes in our code frame, of the probability, that the frequency or the true frequency of the class times let's say, the tendency of the classifier to assign class J once CI should have been the case, The interesting fact is that how can we solve this equation, Well, essentially this is something that is observed in the data. The frequency, the number of times class J has been assigned, This is something that can be estimated by k-fold cross-validation, and which represents the system's bias, the system's tendency to assign a class when another should have been the case, So in a sense, if we estimate this and we observe this, we can obtain this. Indeed, we have... 2 minutes. Yes, okay. Indeed, we have a system of linear equations, one for each Cj, with exactly C unknowns, So essentially, it's a system of linear equations that can be solved via standard means. Okay, so ACC, in a sense, consists of solving this system let's say, consists of correcting the class prevalence estimates, PUDJ, obtained by classifying count according to the estimated system's bias. So it's a very well-known method. Okay, so I would have liked to explain more methods, but I don't have much time left. I just want to mention that another interesting method, which is SVM-KLD. SVM-KLD is essentially a method based on explicit loss minimization. So the idea to use a learner which directly minimizes the error measure used for quantification. This has to do this encounters certain problems because many learners can only minimize loss measures that are linear, while all divergence measures are nonlinear, inherently nonlinear, And in order to do this, we need to record to methods for structured output learning, SVM-perf, a method proposed by Thorsten Joachims is such a method, in a sense, tailored, to use KLD as loss. This is yet another interesting method. I don't have the time to go through Quanet, which is probably the only method which has been proposed up to now that uses deep learning, but I hope you will try to figure out from the slides what it does. I just wanted to mention that, at the end of this lecture, is that there are still several open challenges for quantification. Well, why is this so? Because quantification has not Therefore, there are many open problems. I want to mention the fact that, non-aggregative quantification methods have been investigated too little, and it would be very interesting to further this principle. So this is the kind of method where, where the potential for quantification. Devising transductive quantification methods is also interesting because many contexts are in. It means that all of the which we want to quantify on are already known at training time because these are easier according to Vapik's principle. And again, there has been little research on this. And of course, deep learning. Let's deep learning for quantification, much less than for deep learning in classification or other tasks. And of course, the path principle, we should investigate, explain. There is today to figure out learning methods which are explainable. There has been a big push for classification, but in quantification, the problem is the same, I want to finish these slides in which I list a number of resources, for those of you who might want to work on quantification. So I indicate some software resources, quantification software and data sets, all of big pointers for survey papers on this. So let me conclude, so quantification, learning to quantify the problem that we have discussed today is a relatively unexplored new task with many research problems which are still open, And well, why is it interesting? It's interesting because there is growing awareness that quantification is going to be more and more important because, because of the advent of big data. Because of this advent, application contexts will spring up, everywhere, where we will simply be happy with analyzing data at the aggregate level rather than at the individual level, which is something that we will, in many cases, not be able to afford. Thank you very much.